Welcome to this video about energy, power and efficiency. In the previous one we've discussed that if you create a closed circuit of conductors and apply a voltage source, that current will flow. The amount of current that will flow will also depend on the resistance of the device. Now in essence, an electric appliance is essentially a consumer that converts electric energy into any other form of energy that is considered useful in this case. For example, if you take a light bulb as a very simple example, it will convert electric energy in both light energy and heat, essentially. Only two of these is considered useful in this case. There's nobody who comes home and goes, "Oh, it's a bit cold inside, let me just turn the lights on." While there's nothing wrong with that line of reasoning, it's not what the device is meant to do. You can use electric heating, there's nothing wrong with it, but that would be the actual use of it. In this case, the heat energy is seen as loss of energy, and therefore your appliance is not 100% efficient. And even if you have a device that is meant to generate heat, let's take for instance a water boiler, you would still have a bit of loss of efficiency. Why? A water boiler is supposed to make your water boil, obviously, by heating that one up. But you will still lose a bit of heat energy in the wires and other elements of your appliance. So even those are not 100% efficient. All appliances will create some form of heat when they go through, and this is called the Joule effect. It's not always desirable, however. The amount of heat generated can be calculated using this simple formula or equation. The amount of heat generated is directly proportional to the resistance of the appliance. It is directly proportional to the amount of current that flows it, and you have to square it in this case. And it is directly proportional with the amount of time that has passed. All of these are, of course, used in SI units, so use seconds for your time in this case. Now, a resistor or an appliance also has a certain amount of power associated with it. The more current runs through a resistance, the higher the power generated by that resistor would be. The same logic applies to voltage. Both of these are directly proportional with power, meaning the amount of power a device or a resistor has is voltage multiplied by current in this case. If you combine this with Ohm's law, for instance, by replacing current by voltage divided by resistance, you get voltage squared divided by resistance. Or if you swap out voltage for the multiplication of current times resistance, you can say that the power is amperage current squared times resistance in this case. Now, power is expressed in a unit called watt, one that you should already be familiar with. Watt is also the amount of joules of energy you consume per second in this case. In an electrical sense, it's not a bad thing to write that one down as well alongside of it. It's voltage times amperage, or if we use the derived equations, you would get these two units as the expression as well. Now, a lot of power in a device can be a good thing. For instance, if I were to do some home renovations, I would hope that my appliances, my tools, are powerful enough to do the job at hand. I do not want some light handheld drill that doesn't have a lot of power if I want to go and hang up some shelves, for instance, because you will have a hard time drilling through the wall. However, if I use a very powerful drill, it should make light work of it and go through it quite easily. Now, what determines the power? Well, if I buy a handheld drill, for instance, I would want at least one with 18 volts of battery power, if it's battery operated, because that will be usually powerful enough to drill a hole in a wall. In this case, Although you can also use even more powerful ones. I've seen some with 48 volts even, although that is more professional equipment. But you can assume that the more voltage it requires, the more powerful it is. So power can be a good thing. However, there is a downside to it. A lot of power means a lot of energy used, and that means you will get a fairly large monthly electrical bill if you're not careful. So in some cases, you want your devices to be as power efficient as possible. For instance, your fridge is a device that's going to be on all day. You do not want it to consume a lot of energy. But if you want something like a drill, you do want something that is very powerful, so it depends on your use case. Now, under normal circumstances, the amount of energy you use is measured in its SI unit, as said here, joules. However, 1 joule of energy is a very tiny amount, and an electrical company will have to charge you for the amount of energy you've used. The problem is, 1 joule of power being as small as it is, they can't charge you per joules of energy, because there is no currency unit small enough to do that. Which is why they've invented a new unit to measure your power usage. It's the kilowatt hours. Now, what does this mean? 1 kilowatt hour means a device of 1000 watts, 1 kilowatts, has been used for 1 hour. Because if you take the amount of joules per second that you're using it, and you're multiplying that by a certain amount of seconds, you get a certain amount of energy. Now, what is 1 kilowatt hour? Well, if we're saying that it's 1 kilowatt, meaning 1000 watts, times 1 hour, it is 1000 watts times 3600 seconds. And seeing how watt is joules per second, and you multiply it by 3600 seconds, 1 kilowatt hour would be 3,600,000 joules, or 3.6 megajoules in this case. And that is a more usable amount in practice, because if you run a device of 1000 watts for 1 hour, you will have consumed 1 kilowatt hour of energy. The amount of power gives a good indication of how much that is going to cost with this unit. Here's a simple for instance. You have a TV of 250 watts. It means it is 0.250 kilowatts in this case, right? A quarter of a kilowatt. Now, how many hours of TV can you watch before you're charged €1 by your electrical provider, by your electricity provider? Now, in this case, if I multiply this by 4 hours, right, if I watch 4 hours of TV with this device, I will have actually used up 1 kilowatt hour of energy in this case. 1 kilowatt hour of energy, luckily, doesn't cost me €1 yet. If I want to calculate how many kilowatt hours I can afford for €1, in this case, I take my €1 and I divide it by 0.22 euros per kilowatt hour. In this case, 4.54 kilowatt hours is how much you could use before they charge you €1. If you multiply both of those, you will end up with, quickly type this in, about 18 hours. So that's a very quick calculation for, okay, if I buy a TV, it's 250 watts. I can actually calculate very quickly how much it would cost me to watch TV in this case. Now, there's a few other things, other questionnaires that I would like you to make. You will get a feedback video on those as well. And this one takes into account the efficiency we've previously mentioned. For instance, you have an electric buzzsaw which has 1200 watts of power and an efficiency of 85%, meaning 85% of your electrical energy is converted into kinetic energy for your buzzsaw. The rest, sadly, is heat. Now, try and make these simple questionnaires. I've included the answers, just so you can instantly check for yourself if you've done it right. And you should be able to do the next questions as well. Again, you'll be getting a feedback video on those very soon. Best of luck and see you next time.